Today's video is a continuation of yesterday's Section 2.2 Conditional Statements. A little bit more vocabulary. Equivalent statements are a pair of statements that are both true or both false. A pair of statements that are both true or both false. So you may recall from yesterday, let me go back a slide here real quickly, when we did the last example, the original conditional if-then was true and the contrapositive were true. They are equivalent statements. And both the converse and inverse were false. They're equivalent statements. Well, it turns out that that's always going to be the case, that a conditional and its contrapositive are either going to both be true or both be false. Okay, a conditional and its contrapositive are either both true or both false, and then the same is true for the converse and the inverse. The converse and inverse are either both true or both false. Okay, next thing we have to talk about a little bit is perpendicular lines. This might seem like a little bit of a non sequitur, but we're going to use this as we continue on. So first I need to tell you something about perpendicular lines. If two lines intersect to form a right angle, then they are perpendicular. So if we look at this statement, two lines intersect to form a right angle, that would be my hypothesis. They are perpendicular would be my conclusion. So we're going to write the converse and we're going to decide if it is also true. So if two lines are perpendicular, then they intersect to form a right angle. Okay, if two lines are perpendicular, then they intersect to form a right angle. One thing just to point out real quickly, this little upside down T, that's the symbol for perpendicular, in case you were wondering what that was. Alright, so is the converse true? If two lines are perpendicular, do they intersect to form a right angle? Yes, they do, and that's always going to be the case, so that's true. Okay, so when we have a conditional statement and its converse, if they are both true, then they can be combined into what's called a biconditional statement. So let me fill in the blanks down here first. So if a statement and its converse are both true, then they can be combined into a biconditional statement. Using if and only if. And I can abbreviate if and only if with IFF. So the way we would write that in like notation would be with the arrows pointing at both P and Q. So the way you would say that is, P if and only if Q. All right, so for example, we can write a definition of perpendicular lines as a biconditional statement. I can take the hypothesis and conclusion from up above and rewrite it as a biconditional statement. So, two lines are perpendicular. If and only if they intersect to form a right angle. Another example would be if we were talking about the definition of coplanar points. So coplanar points are points that lie in the same plane. So you can write this as a biconditional statement because the original condition is, you would say, if points are coplanar, then they lie in the same plane. That's true. If points lie in the same plane, then they are coplanar. That's true. So that means we can write it as a definition. Points are coplanar if and only if they lie in the same plane. Oops, didn't mean to have that there. Points are coplanar if and only if they lie in the same plane. Okay, one more example. I'm going to write this one down, and I want you to think about how you could write it as a biconditional statement. A right angle measures 90 degrees. Okay, so write this as a biconditional statement. Pause the video, and when you're done, check your answer. Okay, so to write it as a biconditional, you would have written an angle is a right angle if and only if it measures 90 degrees. Okay, so when we're talking about definitions, in order to be a valid definition, both the conditional and its converse must be true. Both the conditional and its converse must be true. So for example, we can judge the validity of a definition by writing the converse and seeing if it's also true. So for example, A, if an angle is obtuse, then its measure is more than that of an acute angle. So I'm going to write the converse. If an angle's measure is more than that of an acute angle, then it is obtuse. Okay, so is that always true? If an angle's measure is more than acute angle, is it always going to be obtuse? Well, not necessarily, because there are two other possible angles they could be, so this is false. Your counterexample could be either a right angle, which is more than an acute angle, but it's not obtuse, or you could also use a straight angle as a counterexample. And so because the converse is false, this is not a valid definition. Okay, so let's take a look at our second part of our example. If all the measures of the angles of a polygon are equal, then it's equiangular. So I'm going to write the converse. If a polygon is equiangular, then all the measures of the angles are equal. Okay. Is this true? Yes, it is. That would always be true, so that is a valid definition. And because both the conditional and its converse are true, we can rewrite the definition as a biconditional. A polygon is equiangular if and only if the measures of the angles are equal. Actually, it should be if all the measures. Let's fix that. Okay, a polygon is equiangular if and only if all the measures of the angles are equal. And that concludes this video. Thank you for watching.